So when we're talking about liquid chromatography, tandem mass spectrometry, which is what that short form LC-MSMS is, we're basically talking about the pieces of equipment and how they're connected. So the LC, short for liquid chromatograph, or sometimes also called high performance liquid chromatography device, HPLC, is the first part of this instrument, and we're going to talk about that in detail today. This is the part that separates and helps resolve complex, different analytes and chemicals in complex mixtures. And usually with liquid chromatography, this is done with liquid, but you can use other chromatography. There is GC MSMS. I can talk about GC at another point in time, but for omics, we use liquid chromatography primarily, although GC is used quite a lot for metabolomics as well. And in that case, it's gas chromatography, same concepts, but you're separating with gas and really long columns that have absorbent phases. Okay. So like I said, this is really good for separating mixtures of multiple components. So those are the types of samples you're usually putting onto a liquid chromatograph. And basically what happens is there's this pumps that pump two different solvents, solvent A and B, usually two. You can have quaternary pumps. This is a binary system that I'm showing you, where you can have up to 4 different liquids going through the system at one time. And then the mixed liquids run through here. This is your sample injector. So usually the sample gets injected on with the liquids and then through a column. So this is the HPLC column. The HPLC column itself can come with many different functionalities embedded into the column, which then allow you to separate components with different chemistries. And then you've got your mass spectrometer, which is connected to the liquid chromatograph and comes just post column. And usually in between there's something like an interface. And in our case, you have an ion source, and that is almost always what you need for a mass spectrometer. This is the thing that will take your dissolved analytes that are in the liquid and turn them into gaseous ions that can travel through the mass spec. We'll get into all of these details. This is just the overview. And then finally, you detect your analytes with the mass spectrometer. In fact, there's a detector past the mass spectrometer. You can think of the mass spectrometer as more of a filter that moves and guides ions, and the detector is at the very end of that process, which then converts a signal of molecules hitting a detector plate into electronic signals, which then goes to a computer, which processes all that data and puts it in a form that we can use. Okay, so I'm going to talk about a lot of this stuff in detail for the next few weeks, but today we're going to focus mostly on everything up to the HPLC column. All right, so to take a better look at this, I have used this animation a million times, so many of you will have seen it. But basically, liquid chromatography separates mixtures, and in our case, metabolites and peptides, in time based on their affinity for the solid phase, which is on the column, versus their affinity for that solid phase and the liquid that's moving through the column. So you could have mixture going on, and then different types of substances are going to come off earlier because maybe they prefer the water phase, and other ones will come off later because perhaps they prefer to stick to the sorbent column. And then the detector sees the signal, and you get an output. For liquid chromatography, your output always sort of looks like this with peaks, and the peaks, chromatographic peaks, are proportional. The area of them is proportional to the amount of the substance that's run through the column. All right. So let me go through some of these terms that I've been using and give you some more formal definitions. So there's a solid material that's packed onto the column. I've been calling it a sorbent, but let's call it a solid phase or a stationary phase. Normally, these are coated onto very fine particles or spheres, and in fact, the column is not hollow. It's packed full of these spheres, and that maximizes the surface area that the samples can interact with. As well, that solvent phase is the liquid that's running through the tiny spaces in between the stationary phase of the column. And often to get through those tiny spaces, we have to apply a very high amount of pressure. And in some cases, not in our system, but in other cases, you can put so much pressure on the liquid that it actually becomes a gas and moves into a different phase, part of the phase diagram. And that's like another type of chromatography altogether. But you can think like we're talking about really high pressures here. Now, if you perform what's called an isocratic separation, that's when you're using one solvent or the same concentration or composition of solvent running through the system at all times. So you're not running different concentrations of A and B. You're just running all A or all B usually. So this works pretty well, especially if you're just looking for one or two things and you've got a really cool column that seems to work for you. And then you can do pretty quick separations with an isocratic separation. But majority of the time in liquid chromatography, and what really makes liquid chromatography cool, special, and useful is that you can run gradients. So you can start out with a solvent composition that has, say, a high polar, like water, running through it, and then over time change the composition so that you have a more organic phase running through, which is less polar, and it allows you to separate mixtures that have different chemistries. So usually the gradient is really important for good chromatographic separation, and that means separating the peaks. All right, so some other terms. Retention time is the time that it takes for an analyte to elute from the column after injection to detection. So we start measuring retention time at the minute the sample is injected into the system. And then the amount of time it takes for that to go through the system, stick to the column or not, and come off the column and hit the detector is the retention time. The longer the retention time, the greater the solute or the analyte you're looking at has had, the greater the preference it's had for the solid phase. So this is a visual of what retention time sort of looks like practically. So you get these peaks, and we measure retention time from the center of the peak. So the top of the peak is usually the center, not always. Sometimes peaks are shaped a little less symmetrically. And then the retention time is from time 0 until that time that you see the middle of the peak. There's also this really cool sort of space and time, I don't know if it's cool, but it's something to note, called the dead volume. So there's a time it takes just for the liquid to run through the system and before your analyte actually hits the beginning of the HPLC column. So there's lines running from the pumps to the column. We call that the dead volume. It's very important to make sure your dead volume A stays consistent run to run over the many weeks and years if you are trying to compare results over time. If you change one line or one connection line and it's twice as long, you're going to change the dead volume and therefore change the retention times across all of your samples. So we pay attention to dead volume. As well, dead volume can sometimes dilute your sample. So if your dead volume is too large and you inject a sample that has a very low amount of analyte in it, you can get peak broadening and terrible chromatography. So it's always a kind of a goal, although impossible to entirely eliminate, but it's always a goal to reduce the dead volume as much as possible. Peak integration is when we measure the area under a chromatographic peak, which is then used for quantification. And this is calculated simply as half height times peak height, or how you calculate the area of a triangle. Now you may say to me, well, that's not a perfect triangle. How is this going to work? Well, in fact, the math works out really well because I'm not sure if I'm going to get into all the details in another picture or not, but where the curved parts of the peaks curve, you end up usually getting a little bit of the area not under the curve and a little bit of the area under the curve that, if you do some calculus, ends up being the same as if you were just measuring a perfectly pointy triangle with no curves. Okay, so we usually measure width at 50% peak height, and then height from the bottom of the baseline to the very top of the tallest part of the peak. And what you're actually sort of doing here then is measuring a rectangle that's half the width of the peak. And that's exactly how this math works out. Oh, look, I animated that. So that's what you're actually measuring as area. And then when you take these two triangles at the top and visualize rotating them down to the bottom, you end up actually filling out the triangle pretty perfectly. There are multiple algorithms, believe it or not, like 5 to 10 different ways that software can calculate area under a peak. But the most basic way to explain it is how I just did. All right. Sometimes people use height of the peak alone for quantification. They don't even bother doing the area. Just peak height is all they need. This works particularly well, frankly, for mass spectrometry when you have a big dynamic range. But if you have a detector that doesn't have a large dynamic range, meaning how small and how large it can measure things in one run, you might end up finding that you get sort of truncated data or a short amount of area to, or area is not the right word, but if you're trying to do like a linear calibration curve, for instance, you might start losing linearity really quickly at the low and high ends, which means you're truncating your, ability to quantify in a larger range. So usually with liquid chromatography, we talk about peak shape a lot. You'll hear people talking about, oh my God, it just drives me crazy. You talk to any analytical chemist and go to a conference and not necessarily talk about whatever it is you're interested in, like measuring proteins or metabolites or contaminants or cool synthetic oligos. But if you go to an analytical chemistry conference and people are talking about chromatography, they're going to go on and on about peak shape for days. And so we're going to talk about that now. There is usually, ideally, we're looking for Gaussian peaks, just like you would want to see a Gaussian curve for when you're doing any sort of statistical analysis. The reason why is because that peak shape is ideal for calculating peak area. So you're more likely to get an accurate quantification. As well, irregularly shaped peaks usually indicate that there's a problem or an issue with your chromatography system or your column or just the chemistries that you're trying to work with. So when a peak starts out a little shallow, that's called peak fronting. This usually indicates that a column is damaged, that the analyte is not very well retained, and they usually suggest for troubleshooting that you try new mobile phase or replace your column. The opposite of that type of peak shape, where it's shallow on the end, is called peak tailing. Peak tailing usually indicates that the analyte is being too strongly retained. So you have two options, and that's to try a new mobile phase that might help get your analyte off the column a little faster, or to try a new solid phase material. I'd also say it might be that you're injecting just a little bit too much, but that's debatable. All right. This one, which I see all the time in omics because of the way that we actually do things, is called a peak shoulder. So this is when you have unresolved peaks or contaminant peaks interfering with the peak that you're actually interested in. So you can actually picture this as two peaks overlapping. When this happens, and let's say you've got a method that works, you've got a column that works, you've got, you've run it 100 times before. Usually your analyte comes out in this perfect Gaussian peak all by itself, and then you start to see shouldering. They suggest that you try fresh solvent to make sure there's no contaminants in there, or change your gradient so that it's shallower so that you can resolve those peaks. Or finally, and this is actually the best way to do this, if you're trying to develop a method and you just can't seem to get your analyte peaks separated, try a longer column. When I was doing chromatography in my PhD, our columns were so long. I couldn't even believe it. They were like longer than my laptop is wide, which if you've ever seen the chromatography columns we work with upstairs here at Ontario Tech, you'll know they're like 5 centimeters long. It's a really big column. But the longer the column, the better the resolution. Okay. Yes, I'm jumping right into troubleshooting. I hope you guys don't mind. I think it's kind of fun. It gives you an idea right off the bat about why this stuff's important. If you get peak splitting, this usually indicates that you've got an old or really dirty column and the analyte's not being retained very well because the available binding spots are kind of taken up or destroyed. So usually the first thing to do is replace the column, but if you're really stuck, you can try washing it. Maybe you can't get another column. And then peak broadening, usually almost always an indication that there's too much sample. So all you have to do is reduce your injection volume or dilute your sample, and hopefully you'll get a better looking peak shape. So those are like the 5 main sort of terrible peak shapes that you can get and what they could possibly mean. All right, so on a similar note, another thing that's important to people who do liquid chromatography is what's called chromatographic resolution. And I quantify resolution with chromatographic because there's also a concept of resolution in mass spectrometry, which we'll talk about in a couple of weeks. And they're different, but also kind of the same. So the idea here, and if you've worked with a microscope, this is going to be very intuitive to you. The idea here is that two chromatographic peaks are fully resolved when they're separated by some baseline in between. In microscopy, this would be very similar if you have two objects or points that the lens is powerful enough to resolve, but if not, they might look like they're the same object. So that's basically the difference. And so you can actually calculate the resolution of any method, of any chromatography column running a particular set of analytes by actually measuring the distance between your peaks. It involves retention times and peak widths, and it's very intuitive. All right. Why do we care about chromatographic resolution? Well, because as soon as your peaks are unresolved, they're really difficult to integrate or quantify. And then now you're relying on all those algorithms. So in an ideal world, you're going for baseline separation to get good resolution for perfect quantification. I'm going to stop right here, though, and tell you that if you're doing non-targeted proteomics or metabolomics, this is never going to happen, unfortunately. So in fact, we're always relying on these algorithms to give us the best peak shape we can get from data that normally looks very much like two peaks are overlapping with lots of shoulders. Okay, what can you do when you've got unresolved peaks, though? These are the sort of four main, if we're going to call them algorithms or methods for integration. You can keep your baseline to the bottom and drop an imaginary halfway mark between the peaks. You can move your baseline up to the point where the peaks actually touch and basically lose a little bit of the area under the curve. Or depending on your peak of interest. Now, if you're interested in the blue peak, you can drop your baseline down and kind of eliminate or imaginary sort of in your mind, eliminate the shouldering peak and just sort of pretend it's not there and calculate the area of your peak of interest. And you can do that by dropping it from the point where the peaks meet, or you can do it by making an actual sort of Gaussian curve that's imaginary. So those are the four main ways it's done. There are three factors that affect resolution: retention, selectivity, and efficiency. There's a lot of math here. You might be getting intimidating. If you're not really into math, don't worry, I'm not going to go on about this. But K is this factor, which is important to retention. So you can increase your retention by using a weaker solvent, which helps to change sort of the polarity of the chemistry going on of your analyte. You can change the ionization or polarity of the analyte by changing the pH. So maybe it's not retaining well because it's negatively charged, and your column material would do much better binding something with a positive charge. So change the pH and switch that from an anion to a cation. You can also use a stronger stationary phase by changing which again interacts. It's not changing the polarity of your analyte, but it changes the ability of your analyte to interact with the stationary phase. So usually you'll change, if you've been using, say, a C18 and it's not working, maybe you'll go to something that's up like a kind of polar stationary phase, like a helic. All right. Now you can change selectivity by changing the column stationary phase. That's kind of obvious. So, if you want to select for cations, get an anion exchange column, vice versa. You can also change the pH again of the mobile phase, or the solvents themselves. So you could get something that has slightly higher compression, a slightly different polarity. Often our most common organic solvent is acetonitrile, but every once in a while someone's going to switch to methanol and is going to have a huge improvement. So you can increase N, the efficiency, by, and this is my favorite one, by the way, N is plate height. And that's by increasing column length. So again, if you want to resolve peaks that are unresolved, the first thing I would say, because it's actually the easiest, is just get a longer column and see if that works, although not everyone has the money for that. You can also decrease your particle size. By decreasing the particle size, you increase the surface area and the available binding sites in the column. it also increases the pressure on the column, but it also increases plate height. And then finally, if you reduce your peak tailing by altering things like the solvent and the stationary phase, you might actually just be able to increase your efficiency and your resolution by making sure your peaks are no longer tailing. Another fun thing to do is to increase temperature. So we do this, we run our LCMS upstairs, has heaters built into the column compartment. And actually, I think most LCs come with heaters now. This is like, you know, antiquated if you don't have one. Everyone, it just automatically comes with any kind of liquid chromatography system. Anyhow, if you increase the temperature, you actually change the sort of density of the solvents running through the system and their compressibility, and therefore the pressure, and therefore the way that the analytes that are in the solvent interact with the solid phase. And so increasing temperature usually reduces pressure, but allows you to run solvent through the column faster, which also increases plate height. And then finally, you can reduce extra column volume. So that would be by sort of getting, and also system volume. So that would be, again, we're talking about things like reducing dead volume, but also making sure that the volume of your column, this happens when you decrease particle size. You usually get more particles in there, so then you have less volume inside. This one's kind of actually unintuitive to me, and I have a hard time explaining it, frankly. I don't know why that would necessarily do anything except for just prevent your analyte from being sort of too dilute. I feel like there's a million better ways to fix that problem.